Hello, welcome to EE5508 Semiconductor Fundamentals. My name is Wu Yihong. I will be teaching the first part, and then Professor Chuo will take over from the second part. My room number, phone number, and then email are written here. If you have any question throughout this module, please do write me an email. So today is the first lecture. I will give you a brief introduction about this module. So first of all, so why semiconductors? So I would just want to use this one slide to explain the background, all right? You can see what's shown here that you have an atom. So inside the atom, and then you have a nucleus, right? And of course, you have a number of electrons which are moving around this nucleus, right? So, and of course, the electrons are bounded to the nucleus by a Coulomb interaction. This Coulomb interaction actually is a quite strong interaction. So that's the reason why, in the normal environment, these electrons cannot escape from a nucleus, right? And however, if you can find ways to make electrons escape from nucleus, for example, by supplying additional energy to the electrons. And then if the energy is high enough, and then some of these electrons will be able to escape from nucleus, right? So once the electrons come to the free space, and then of course you can find ways to control it, and then you can make electronic devices, right? So typically, for example, if you have an electron, let me see if I can use a whiteboard to explain this. Okay, let me try to whiteboard. Okay, so so basically for all the electronic devices, so what's the fundamental to electronic devices? Basically, you have a device which you can control the current flow, right? So what's current? Of course, you know that the current basically is the flow of charge, right? Say, for example, if you have an electron like this, and then so once this electron is in vacuum, and suppose this electron have an initial velocity like this, and of course, if you don't have any collision or friction from the environment, and then this electron will just keep moving, right, in the same direction, okay? And of course, now you put the detector here, and then you can detect, how many charges which will reach this detector per unit time. That basically is your current, right? And so, to make a device means that you can control the movement of the charge. Say, for example, if you put another two electrodes here, say, for example, this is grounded, right? And then this, of course, you can apply a bias. So if this bias is positive, and then you know that this electron will be attracted, right, to this electrodes. So once it's attracted to this electrode, of course, the number of electrons which you can detect the detector will be smaller, right? So of course, if the bias is strong enough, you make all the electrons to deflect into this side electrode, sometimes we call gate or grid. And then, of course, the number of electrons which you can detect, the detector will be 0. So this is equivalent to say that you can turn off this device because the current will be 0, right? So this is just a very simple device. And actually, this is called vacuum tubes. And so in principle, you just need a electron source, and then you need a detector, and then you just need a grid or gate to control the motion of electrons in the free space, right? And then you can realize a very simple device. But of course, such kind of device is very bulky, and so that's the reason why we need another way to do it. So the other way to do it is quite straightforward. So what you do that you just need to find a material with which can provide the free electrons, right? So for example, if you have a standalone atom, of course you have electrons, moving around this nucleus, right? And then of course electrons cannot escape from this nucleus, right, due to a very strong Coulomb interaction. And however, if you have many this kind of atoms, and then under certain conditions, right, and the suitable conditions, and also you have a right number of electrons moving around this nucleus. This means different type of atoms. So eventually, you may form a material. So this means that all these electrons from different atoms will come to interact with each other, right? So when during this interaction, and of course, some of these electrons will become movable, right, inside this material. So if this is the case, and then you have a metal, right? So so for example, you have a copper, say gold, and then aluminum. So of course, you have many other examples. So all these are very good metals, or very good conductors, right? So in this case, of course, you have a large number of electrons per unit volume in the metal. So of course, you may think that so if that's the case, and so how about just apply a bias? This means this is a piece of metal, right? And then I just say connect this one to a battery, right? And then so connect together. So in this case, and then you may think that the current will flow, right? So this is the current direction because you have movable electrons inside the metal, right? So of course now you may think, so why not I just put another electrode here, right? And then see maybe I just grounded this one, say for example. Of course, can put additional electrodes, and then see you just apply bias to this, right? And then you may think that if that's the case, I should be able to deflect electrons. For example, if I apply positive bias here, I should be able to deflect electrons into this direction, right? And then in this case, in principle, I should be able to control the current flowing in the circuit, right? So this will form a device. This, of course, you know that this does not work, right? So what happens is that because inside the metal, you have too many electrons. So that's the reason why when you apply this kind of a bias, and then immediately, so of course, you will cause some movement of electrons, for example, near the surface, right? But once you have electron move in this surface, because you have huge number of electrons per unit volume, and what happens is that immediately you will establish a backward electric field, which will counterbalance the external electric field which applied through this bias. And then that internal electric field can be very, very strong because screening field, right? And then the screening length basically is a region from the surface which you can have some sort of control over the electron density is very, very small, okay? That's just about maybe 1 angstrom. It's dependent on the electron density inside the metal. So if that's the case, say for example, if that's a 1 angstrom, right, and then this total width of your metal thickness is, say for example, and this is say 1 micron, right, and then so 1 angstrom or 1 micron, you can see that the change which you can cause to the current by applying external bias in this case is extremely small, right? So so not to mention that you can switch off the current, of course, not possible, right? So that's the reason why, although metal is a very good conductor, and unfortunately you cannot use metal to build electronic devices. So metal at this moment is only good as a conductor, right? So of course metal is very useful because you need to connect different devices together to form a large scale circuit, right? So that's the reason why metal, although you cannot use it to function as an active part of the electronic devices, but it's essential for connecting all the devices together, right? So that's the reason why people basically come out this semiconductors. So what is semiconductor? So semiconductor, of course, in most cases, we're only interested in solid state semiconductors, right? Actually, in most cases, all the semiconductors are solid state anyway. So it's just like metal; it's a solid state material. But there's a huge difference between the metal, in the sense that the electron density, and actually we call carrier density, because in semiconductor, actually we have 2 types of carriers. One we call electron, the other this is the missing electron. So missing electron we call hole, which is positive charge, and then the electron basically is a negative charge, right? So the carrier density inside semiconductor can be controlled by external means. So this means that we can control the carrier density inside semiconductor to be at a level which is much, much lower than the electron density inside the metal, right? So when this happens, and then when you apply external field to the semiconductor, and you can actually modulate the carrier distribution inside the semiconductor, right? And also you can basically make these electrons or holes move in different directions. So, and then of course, eventually you can control the motion of electrons or holes in a predefined direction, and in which you want to have electric conduction, right? So that basically is a simple switch, okay? And so what's good about the semiconductor that in addition to the flexibility in controlling the carrier density, as I just said, you have two different type of semiconductors. So one is called P-type, so in which electric conduction is mainly determined or dominated by holes which are positively charged. And then we have the other, basically N-type. So N-type is dominantly, the electric conduction in N-type semiconductor is dominated by electrons, okay? So what's good about these two type of semiconductors is that when you put the two type of semiconductors in contact with each other, and then you form something we call p-n junction. Okay, you will learn this one in other modules. And so once you have this p-n junction, and then people find that actually electric conduction through this p-n junction is dependent on the polarity of the bias which you applied to this p-n junction, right? So for example, if you connect this p side of this p-n junction to the positive terminal of your battery or power supply, and then N to the negative terminal, and then in this case, and then current actually can flow through this p-n junction. And however, if you connect P side to the negative terminal of your power supply, and the N side to the positive terminal, and then the current cannot flow. So this means that this basically is a switch. And then you may ask me, so what's the difference of making or using a mechanical switch? Because mechanical switch can actually completely turn the current on and off, right? Of course, there's a huge difference because a mechanical switch, although it's very good, right? So the on-off ratio is almost infinity, but you cannot make it very, very small, okay? So, and then the p-n junction wise is good because you really can make it into a very, very, very small device, right? So once you can make it into a very, very small device, of course, you can integrate a huge number of devices together to form a large-scale integrated circuits. Of course, and then you have more functions, right? And then, a p-n junction, basically you can see that we call two-terminal device because you have a P and N, right, two terminals. So two-terminal device cannot amplify a signal. So why this is the case? This is because that, maybe I just go to this white screen again. So a two-terminal device means that, so you have, so there's the input and then this is the output, right? And so, for any electronic device to work, you have to excite the device. I mean, so excitation basically is done by supplying a current to the device, right, from external battery. So of course, from external battery, where do you get the current? Because you use electromotive force to move electrons inside the conductor, right? So this means that it's difficult for you to amplify the signal. You know why? Because for example, if this is a power supply, all right, and then you connect your signal here, so your signal maybe can be DC or AC signal, right? So in this case, why you cannot amplify a signal? Because you get output from here. So your output and input are on the same line, right? So you know that so current flow in the closed loop, at any point of this closed loop should be the same, right? Due to this charge continuity requirement. So this means that if your signal has a certain amplitude, and then your output has exactly the same amplitude. So this is the reason why you cannot amplify this. And however, if you have a three-terminal device here, so now you don't need to put your signal here, right? Three-terminal. And then so what you can do that you can actually connect your signal to this terminal, right? And then if you can use this signal to control the current, okay, control the current passing through this device, and then of course, so eventually, and even the your external power supply, which will provide same level of bias, to this device. But so how much current can flow through this device is controlled by this third terminal. Your third terminal is connected to your signal. So that's the reason why your signal actually, if you can form a device such that when there's a small change in this terminal, it will give you a very large change in this path of a circuit. And then of course, you get amplification. Why? Because eventually the current flowing through this, the path will change proportionally to your signal. But the overall current in this branch or path of circuit is much, much larger than that in this control terminal, right? So that's the reason why it's a three-terminal device is suitable as an amplifier, right? Of course, and at the same time, the three-terminal device can also be a switch, right? Because you can actually use the gate to completely, maybe not very completely, but nearly completely, to turn off the current in this path, right? So this means that your three-terminal device will have more flexibility because you can use the three-terminal device as both amplifier or as a switch. But two-terminal is dominantly just a switch, right? So once you have a semiconductor, we have two types of three-terminal devices we call transistor. So the first one we call NPN. So basically have an N-type semiconductor, P-type, and N-type. We'll not go to details, but anyway, and you can have a three-terminal device because the two N's serve as two terminals, and then P will be the third terminal, right? And then you can also form this kind of lateral structure, and then you have so this is not very clear here, but anyway, and then you have for example, P channel here, and then you have this source and drain, and then you have N adopter region, and then on top of this channel, you may put the oxide, and after that you deposit a gate here, and then so this gate will be a third terminal, and then the other two terminals here. We're not go to details, but anyway, this is called a MOSFET. So it's the most single important device in electronics. And of course, when you learn devices, then you will learn this part. Okay, but anyway, so you can see that once you have this kind of simple discrete devices, and then of course, since these are solid state materials, so you can make all this into a very, very small device. And then after that, you can integrate all this device to a very large scale. And then of course, you have this large scale integrated circuits, right? So of course, you need all this for your computer, right? So both as CPU or as a memory, right? And then, so this actually is the first transistor. You can see, sorry, and this is the first transistor, and so made by Bell at that time. This was done in 1947. And of course, the device is very bulky. It's handmade. And then this is the first sample of integrated circuits proposed or done by Dr. Kirby in Texas Instruments, right? And by the way, so both work were awarded a Nobel Prize. Okay, and of course, this is what we have now in our computer, right? So this kind of device, you can see, is very important for information processing. And of course, we also use all this electronic device for information storage as well, right? But the information processing right now is dominated down by this kind of electronic devices, right? So the semiconductor is good, not just because that you can have electronic devices. You can also use the semiconductor to implement this kind of photonic devices. So basically, it's a source for light. And we have two different types of light sources. One we call spontaneous. It's just the light from a light tube. And so what happens to this kind of light is that so light basically comes from the recombination of electrons at the different energy levels. This basically is from quantum mechanics, right? So, when all the electrons jump spontaneously, this means that the different electron will jump to the ground state at a different timing, and then eventually you get something we call a spontaneous light. This means that the phase of all this photon or light emission is not the same or not synchronized. And we can have another type of light, basically we call laser, in which the phase actually is synchronized. So in this case, we have a coherent light, just like a laser, right? So both the spontaneous light source and the laser can be implemented by using semiconductors. So for the spontaneous light, we have this light emitting diode we call LED. I think some of you may know this. And of course, for laser, we have the laser diode. So it's the same type of p-n junction or a little bit complicated p-n junction. For example, you may have a multi-layer, not just two layers. But anyway, eventually you can have a laser from the semiconductor structure. So you can see we can have a laser either from the edge of this p-n junction or from the surface, right? And then we have different type of lasers. So all these are very, very important for many real applications, right? So of course, the immediate application at that time was for communication, right? So in our electronic system, of course, information processing is very, very important, right? So, but after you process the data, so normally what do? You want to transmit the data to somewhere, or you store this information in your local device, for example, your PC or laptop, right? So to store information and actually, of course we can use electronic devices, right? For example, now when you buy your device, you have all your electronic devices basically have electronic memory. But of course, many of the electronic memory are so-called volatile. For example, DRAM and SRAM, you can store information temporarily, but since it's volatile, so you cannot have a permanent storage, right? That's called memory. But we still have this called secondary storage or master storage. And then, light can help is because that you can use this semiconductor laser to implement optical disk drive, right? Of course, now we don't use so often in the computers, but see maybe 20 years ago or 15 years ago, and we still use, say, for example, DVD and the Blu-ray in our desktop PC, right? And of course, in laptop at that time we also use optical disk as well. So that's for storage, and then for information, of course, display and also communication. I already mentioned, right? It's very important because you need to transmit the information from your local device to the network, right? So that the data can be shared by others, or you can get data from the network so that you can after you can process using your local device. So of course, information transmission, you don't need to use a light. You can always transmit information, say for example, using copper wire, right? But the copper wire, the problem that you have a bandwidth limitation. This means that you cannot transmit data at a very fast speed, right? Because the bandwidth is narrow, it's not very wide. And then, of course, except for the copper wire, and then you still can use RF, say for the microwave, right, radio wave. But again, the amount of information which can be transmitted is always limited, right? So that's the reason why for intercontinental, or even of course in our so-called smart home, and so we also use optical fiber, right? So the optic fiber is very good because basically light are confined inside the fiber. Okay, and so light can propagate very fast, and then since it's light is propagating inside the fiber, it will not be blocked by buildings, or mountains or whatever, right? So that's the reason why this optical fiber communication is still very, very important. And then of course you can use other type of lasers, but they are very bulky and very expensive. So, and also it's difficult to control, right? So this means when you do this communication, you have to switch the laser on and off at a very fast rate. And the semiconductor laser is really good at this, and then it's low cost, compact, right? And also you can modulate the laser at a very high frequency, right? So that's the reason why this kind of semiconductor optoelectronic device is very, very important, right? And then, so the next area which is semiconductor can play a very important role, and of course is the information storage, right? I already mentioned that you can have all these different type of solid state memory, but the semiconductor, of course, you have DRAM and SRAM, but remember And if you want non-volatile storage, you can also have this flash memory, right? So all these are basically implemented by semiconductors, right? And electrons actually, that have both a spin and a charge. So far for electronic devices and optoelectronic devices, we mainly focus on the charge of electrons. But if you can control the spin of electrons, and of course you can have additional functionality, right? And so far, electron spin in certain type of materials we call magnet, and so which can be controlled. And then of course we can make use of this. That's because that inside this kind of magnet, for example, ion. So what happens that so the spins of all these electrons interact ferromagnetically, and then because the interaction actually is very, very strong, it is a quantum mechanical interaction. And then so when you have a suitable material and such that the inside this material, for example, ion, so all the electron spins are automatically aligned in the same direction, and then you have the electromagnet, you have the magnet. So the magnet, that you can have something we call magnet moment or magnetization, which is magnet moment per unit volume, and then magnetization has a direction, right? So that's why you can call one direction equal 1, that direction equal 0. So automatically, this will be information storage cell, right? But so far, we can only realize this kind of, and of course, in addition to information storage, we can also have different type of devices. So for example, we have the spin valve or magnetic junction. Anyway, I will not go to details. And so, but all of this can only be realized in metallic systems, right? And then, of course, we have been using this kind of spintronic devices in hard disk drives, which is still very, very important. So now people are working on this non-volatile memory, which is also based on this kind of spintronic devices, right? So why do I need to mention about this one? Since this module is about a semiconductor. So this is because that in future, and so if you can have a material which is a semiconductor and at the same time is also a ferromagnet, and then you can realize many new type of devices. That's because that you can use semiconductor for electronic processing or for optoelectronic devices, and then you can use the magnet property for information storage, right? So many years ago, there have been a lot of activities going on and about this magnetic semiconductor. And so unfortunately, so far, we can only have one or two types of semiconductor which can be made ferromagnetic, right? But the temperature at which this semiconductor can be a ferromagnet is typically quite low. And so at the moment, highest temperature is just about 200 Kelvin, right? So that's why at the moment, of course, we cannot use this one for practical applications, but in future, if this kind of magnetic semiconductor is realized or is found, and then at room temperature, and then of course, I believe it will have a huge impact on electronic and optoelectronic devices. So then I still have one error here, which I need to mention. And so when we talk about electronic devices, optoelectronic devices, or spintronic devices, and so we are making use of quantum mechanical properties of electrons, right? And however, we make use of this, and in a certain sense that quantum mechanics is playing the role inside these kind of devices, but the device itself is still semi-classic, or is based on semi-classic or classical physics, right? But in future, and then we'll have this kind of so-called pure quantum devices. So the quantum devices, and then of course the minimum unit for this kind of quantum device we call qubit. It's different from the electronic bit or optical bit or magnetic bit we're talking about in classical devices. And so the qubit basically you have two states which are entangled, right? And so and they basically can process, store, or transmit information purely in a quantum mechanical manner. And of course, if you can realize this kind of device, you can do many things which classical devices cannot achieve, right? Due to this parallel processing capability of quantum mechanical devices, right? So of course, semiconductor. Right now, I think for quantum electronic devices, we mainly use, for example, superconductors and the photons. And of course, in future, spin can also be a very important um, object, right, for realizing a platform, okay, for realizing this kind of quantum electronic devices. All right. So, but anyway, and so of course, semiconductor definitely will play a role, right, eventually. But in this module, we'll only focus on okay, part one will focus on fundamental properties of semiconductor for electronic devices. And also, of course, we'll talk about energy quantization, which will be very important for optoelectronic devices. And then the second part, and Professor Tour will mainly focus on this optical properties of semiconductors and how the semiconductors can be used to realize this kind of optoelectronic or photonic devices, right? Okay, and so now, what's a semiconductor? And of course, you can guess from the name of a semiconductor, right? So you know what a conductor is, right? Conductor basically is a piece of material which can conduct electricity, right? And a semiconductor means that it can conduct electricity, but the conductivity of such a material, so typically is not as high as a metal, okay? And then, but most importantly, that it's controllable. So this kind of material basically called this semiconductor. And of course, in addition to metal and the semiconductor, we have a third type of material we call insulator. All the semiconductors actually, after you finish this module, you will know that all the semiconductors at a very low temperature are also insulators, right? So that's why we only compare this at the room temperature or around room temperature. So around room temperature, of course, semiconductor is different from an insulator. So insulator basically is an insulator even at the room temperature or at the elevated temperature. Of course, low temperature is an insulator. But semiconductor has a conductivity which depends strongly on the temperature. So at low temperature, the conductivity is very low. It's just like an insulator. But at high temperature, then it's quite conductive. Okay, and then so metal on the other hand is always conductive, no matter it's at the low temperature or high temperature, right? In fact, at low temperature, it conducts electricity much better, right? Okay, if you look at the typical resistivity or conductivity of a selected group of materials, as you can see here, metal. So we have silver, copper, gold, aluminum. So these are very good conductors. So if you look at resistivity, very low, and the conductivity very high, right? And then we do have other metals which are conductors as well, and resistivity is not very high, and then conductivity is not very low, but definitely is not as conductive as this group of material, right? We'll not go to details, but anyway, all this depends on the carrier scattering process inside all these different type of materials, right? And so, and then of course we have this different. Okay, so all this is called elemental, metals, right? So if you mix some of this metal together, you can have alloys with different type of property, right? And so you can actually control the resistivity and the conductivity. At the same time, maybe you can improve the mechanical property or chemical property, right? For example, some of these might be might have very good mechanical property. Some may have very good chemical property. It means that it's not so easy to be corroded, for example, right? And of course, some will have a very good temperature, very so-called very low temperature dependence. It means that when temperature change, and then conductivity will not change a lot, will not change largely. So this basically is sometimes we have to make alloys using different elements. And then of course the next group we have semiconductors. You can see we have carbon, germanium, and silicon. So these are the so-called group 4 semiconductors. So later we'll talk about this one. And so for semiconductors, so don't need to worry so much about the values given here, and so all these values can be varied, right? Either by doping, which we'll talk about in lecture 5, or by light irradiation, or by temperature. So basically, it's controllable. Okay, and then we have insulators. So the insulators, of course, you can see that the resistivity is very, very high, right? And then conductivity, of course, very, very low. Okay, so of course, these kind of materials are still very useful. You know why? So as I said, that a semiconductor, you need semiconductors for making an active device. But when you have many devices which you want to connect it together, and then of course you need metals, right? And even for single device, you still need metals as electrodes, right? And then so insulator means that when you integrate all these devices together, and of course you have to have electrical isolation, right? So this means that you need the insulators to separate all these devices. And of course, even for a single device, you cannot form a single device just on top of the metal, right? Because you have a short circuit. So you still need the insulating, something we call substrate, insulating material, and then so that you can fabricate an electronic device on this kind of substrate, right? So basically, all this material will play a role. Okay. Now, so what are the major type of semiconductors? Okay, and we have so basically we have a semiconductor for electronics, optoelectronics, and spintronics, which I talk about, right? So of course for electronics, and so we have first we have so-called group 4 semiconductors, and so here we have carbon, silicon, germanium, and tin. And the first transistor was made by germanium, right? And however, a single type of semiconductor alone will not be able to make a very good electronic device. And then, so typically you need an interface with other materials. And silicon is very good, and it's because that silicon can form a very good interface with silicon dioxide, right? That's very important. And then that's the reason why, for example, for CMOS device, for MOS device, and so that's very important that you have to have a very low defect interface between silicon and silicon dioxide. But germanium is very difficult to have, for example, germanium oxide interface is not as good as silicon, right? So this is one reason. Of course, the other reason that germanium has a relatively small band gap. We'll talk about band gap in later part of this module. And then so once you have a smaller band gap, and then your device is more sensitive to temperature, right? So this is something sometimes we need to avoid. And then so that's the reason why silicon is somehow is abundant, and then it's just suitable for making this kind of electronic devices. And so of course, and so germanium has advantage as well, because the electrons inside germanium can move faster than that in silicon, right? And then so as a whole as well. So that's the whole as well. So so that's the reason why, and many years ago, then people are trying to, for example, to form a silicon germanium alloy or silicon germanium in heterostructures, and then so that you can make a much faster device, either by making use of electrons inside the silicon germanium or germanium, or by using the strain. So there's something maybe now it's difficult for you. So if you can apply a strain to silicon by growing silicon on germanium, and then you can actually reduce the effective mass inside the silicon, and then so that the electron can move a little bit faster, right? So that's why a lot of engineering has been done in order to improve the speed of electrons inside silicon. Okay. And then so on top of this, you have carbon, and carbon is a very interesting material. So you know that in the bulk, the carbon can be in the form of a diamond, right? Diamond actually is a very good semiconductor. So although the band gap is very large, so that's why in principle you can consider it maybe as an insulator, but anyway, it's a semiconductor, all right? And then you have a graphite. The graphite is a semi-metal, okay? And then, so what's really good about the carbon is that you can make carbon into all sort of different type of nanostructures, right? So some of you may know. So you have a carbon 60 and carbon nanotubes, and then now most importantly you have a graphene, right? So graphene is a single layer of graphite, and then electrons inside graphene can behave totally differently from electrons inside other materials, right? So that's the reason why you can find many interesting phenomena, which is very interesting from a fundamental point of view. And of course, you can also make use of this for some practical applications. And then what about tin? And the tin actually, you can use this tin for optoelectronic devices. So this means that if you can, so silicon and germanium, they are not good for optoelectronic devices because they are in direct bandgap semiconductors. Now, of course, difficult to understand. We'll understand this, once we learn semiconductor band structure in this module. So, but anyway, now you just need to know that silicon and germanium are not good for optoelectronic devices. And tin can be used for optoelectronic devices. So that's why now people are working on integrated opto and electronic devices by making use of group 4 elements. Okay. So now we still have other type of semiconductors which can be very good, can be used for very good electronic devices. So this is called group 5. So group 5, you can see this is a compound between group 3A and then group VA elements, right? So we have many examples here. For the most typical example is gallium arsenide. So gallium arsenide is very good for optoelectronic devices, but it's also very good for electronic devices. So you can use gallium arsenide to fabricate very fast electronic devices. And however, why people didn't rely on 3-5 semiconductor for large-scale integrated circuits is because that the process is very complicated, and also it tends to be very expensive, right? And many years ago, I think in the 1980s, and then the Japanese company, the Fujitsu, has built a very large fab, right? So wafer fab for manufacturing 3-5 based gallium arsenide based electronic devices. But so eventually, of course, it couldn't compete with silicon, right? And then of course this is 3-5. You know that is very good for optoelectronic devices, right? But anyway, before that, we should look at for electronic devices. In addition to gallium arsenide, you have some other semiconductors, and then you can really have a very, very fast electronic device making use for example, this gallium arsenide and then indium arsenide, basically semiconductors with very, very small band gap. But the problem that you cannot use this kind of device at a normal temperature. You have to cool down, right, to very low temperature because the band gap is very small, right? But they are very good for, So these are very good for optoelectronic devices. So in fact, the first LED and our laser dot was made from gallium arsenide, right? But gallium arsenide, the band gap is quite small, so that's the reason why, for example, if you make an LED over laser dot using gallium arsenide, and then so the color you will see basically is in the near infrared, right? So that's why in order to have a visible light emission from semiconductors, you have to use other type of semiconductors. So that basically, at that time, people look at a gallium phosphide, for example. So this will give you green to a yellow light, right? And then if you use, let me see, and the red light. So if you have this gallium arsenide and gallium aluminum arsenide, right? It means making this alloy, and in principle you can get a red light as well. But the efficiency is not very good. Okay, so so that's the reason why in the 1980s, okay, there were a lot of activities on the 2,6 compound. For example, you have a zinc selenide as a typical example, zinc sulfide, and then zinc telluride. And then, so this kind of material, and so in principle, in terms of band gap, you can really make optoelectronic devices using this kind of compounds, and then the wavelengths will be in the green or blue region, right? So in fact, at that time, many large companies are in Japan, and we're working on this, but then from Sony to Panasonic and Sanyo or Sharp, right? And of course, in Europe, you have Philips So they were all working on this kind of semiconductors. Of course, in the US at that time we have 3M. But in fact, my PhD was about this blue-green laser using 2,6 compounds. And of course, at that time, we managed to demonstrate blue-green laser by optical pumping. But electron injection was very, very difficult at that time because we couldn't obtain very good p-type semiconductors. And then most of these semiconductors can be made as n-type, but p-type were very, very difficult, right? And at the same time, of course, in Japan, there were 2 groups. Of course, in other places, maybe just few groups, or very, very few groups, working on gallium nitride. So gallium nitride is another, semiconductor, which, of course, can be used to make a blue or even UV LED or laser diode. But again, it was very difficult to make both p-type and n-type semiconductor at that time, right? And then suddenly, around 1991 or 1990, you heard about this story, right? And there's a small company in Japan called Nichiya Chemicals. And then in this company, there's a Professor Nakamura. And of course, at that time, he was a researcher in this company, and after that, he became a professor in UC Santa Barbara, right? And then he developed a process, and so which can which could successfully obtain both p-type and n-type semiconductor. And of course, after that, they actually demonstrate LED and also laser diode in the blue and the UV region using gallium nitride and also gallium nitride with other type of compounds, right, with alloys. And of course, after that, you know that the whole LED industry has changed, including the lighting industry. Just because of this great invention in this field. Okay, so of course, and later, a few years ago, so Professor Nakamura and also Professor Akazaki and then another professor, I cannot remember his name, and they were awarded Nobel Prize, right, for this great invention. Okay, and so that's about this 3.5 and then 2.6 semiconductors for optoelectronic devices. But I don't remember. And so we still have a wavelength region which cannot be covered by this kind of semiconductor. That basically is we call a wavelength in the, say, 20s or 20 to 30 micrometer, that kind of range. So for this kind of very long wavelengths, these are light source, which is actually very important for certain studies. For example, when you have to study for atmosphere study, it means the light light with this kind of wavelengths can penetrate through atmosphere, right? So so this kind of study, so typically you need a light source with very long wavelengths, and then so we do have this so-called this 4-6 compounds. And I'm sorry, I think this this arrow is like this is not sorry, 4-6. Sorry, here this one. Okay, so 4-6. For example, you have just give you an example like this tin telluride, right, or lead telluride, and then lead selenide. So all these kind of materials can be used to fabricate optoelectronic devices with a very long wavelength, right? So that's why you can see that for optoelectronic devices, we do have a lot of semiconductors which can be used, right? And so now, in recent years, there's a huge development in this field we call topological insulators. So what's this kind of material? This kind of material is very interesting. And so they are basically insulating inside the material, but conducting only on the surface, right? And so, and also electrons moving inside this kind of material on the surface, and so can avoid some of the defects or impurities. So this means that in principle, if you can find a suitable material, and actually electron can move only in one direction, right? So of course, in this case, and then you don't have a large angle scattering or back scattering, and eventually and this will make the device, very efficient, and also electron can move very, very fast, right? But if you look at this kind of materials, this now this actually the most prototypical material for this kind of a topological insulator, and actually is let me see, a bismuth selenide. So here it's not typical; it's very difficult to see. It's a bismuth selenide or bismuth telluride or antimony telluride, and it's very interesting that this kind of material we call 5,6. And actually, this kind of material are very good thermoelectric materials. So it means that you can use this kind of material to generate electricity from a temperature gradient, right? And so that's the main application of this group of materials so far. But since maybe less than 10 years ago, maybe about 10 years ago, and then people found that actually this kind of material can be this topological insulator, right? So that's why. So sometimes when you do research, and it really depends that suddenly an old material become a completely new material, right? So the old material means that during that stage of development, people only knew that this kind of material, say for example, can be used for thermoelectric conversion. But at that time, of course, people didn't know that this can be a topological insulator, right? So what happened that, of course, this is not some sort of so-called standalone development in this field, and not because that suddenly people found that this kind of material can be a topological insulator. It actually was stimulated by the development in other area we call spintronics. Okay, so and then during that kind of development, and then eventually it leads to the discovery or understanding that and this kind of material actually electron inside the material actually can behave totally differently, right? So that's why this kind of technology or scientific development sometimes is quite interesting. And then after we have been working in one direction for some time, and then suddenly realized that we need to come back to relook at some of the issues or materials which we worked before, and then suddenly realized that we missed out something, right? So since many of you are doing research, maybe you will already have encountered this kind of the same thing before, right? Sometimes can be very useful. Okay. Okay. Now, very recently, and there's another huge development in this field, semiconductor, we call two-dimensional materials. So this two-dimensional materials, of course, if you look at all these semiconductor materials, of course, people have been trying to form all different type of quantum mechanical structures. So we'll talk about this one in this module, and see, for example, if you can sandwich one semiconductor with a narrow band gap by another semiconductor with a larger band gap, and then you can form a quantum confinement. Of course, if you can reduce the thickness to a certain range, right? But no matter how narrow the quantum well you can form, and it's still though it's two-dimensional, but still not so-called completely a two-dimensional system. But if you can have a material which is only one atomic layer or one monolayer thick, and then in principle you have some sort of perfect 2D confinement, right, or 2D system. And then this kind of material actually can be formed by peeling off some of the material layer by layer, right? So of course, the best candidates for peeling off layer by layer, of course, would be materials which naturally have a layer structure. And such kind of material actually we have many. And then, so one type of this basically called this a transition metal chalcogenides, right? So this chalcogenides basically is a compound formed by all these transition metals with a group 6 element here. All right. Of course, we have others as well. Okay, and then due to different combinations, now we have a huge number of materials, right? So which we'll talk about in the next slide. I think the last type of semiconductor which I forgot to mention is semiconductor for spintronics. So, so far the most successful magnetic semiconductor is a gallium arsenide doped with manganese. Okay, when you dope gallium arsenide by manganese, you can make this gallium arsenide ferromagnetic up to about 200 Kelvin, right? And of course, people are trying to stop all different type of semiconductors by magnetic impurities. And some claim that they have found room temperature magnetic semiconductor. But all of these and all of the claims eventually are unverifiable. It means that, of course, many people claim that they can this is indeed a room temperature magnetic semiconductor, but so far, and you all this in the claim is basically maybe people have found some sort of magnetism about room temperature inside semiconductor, but you don't have this global ordering, right? So that's the reason why, and the so-called true magnetic semiconductor so far, most people believe that only in gallium arsenide adopt the manganese. Okay, and of course, and we cannot predict what happens in future, right? So that's why in future, maybe people find a way to make many semiconductors into a ferromagnet, right? So we don't know. We'll see, what will happen. Yeah. So of course, when this happens, and then this will have a huge impact on the semiconductor industry, right? Okay, then we turn to this 2D. Okay, sorry, this is a 3D. Okay, 3D type of semiconductor. So now what's shown here that you have the band gap, and as a function of lattice constant, right? And so this band gap, actually, you can see the color here. So this color basically indicates that if you make optoelectronic devices using all these compounds, so these are the colors which you would expect, right? For example, if you want to have a UV device by using semiconductor, and then you have a gallium nitride, which is one of the choices. Of course, it's the top choices, right? So now people have already realized this. And of course, you still have a silicon carbide as well, right? And then the blue region, and then you may have all the 2,6 I just mentioned, zinc selenide, right? And then so cadmium sulfide, okay? And then green region, you have this aluminum phosphide. And then yellow, you have gallium phosphide, as I mentioned before. And then red, of course, you have this aluminum arsenide, right? Or alloy between gallium arsenide and aluminum arsenide. And then pure gallium arsenide is near infrared or infrared, right? And although silicon and germanium are given here, so these are not for light emitting devices. But silicon and germanium are not good light emitting devices. These are actually for photo detectors, right? So basically, the band gap is corresponding to this kind of region. And of course, you do have some other 3-5 semiconductors, indium arsenide, gallium arsenide, indium arsenide. So you can see this is indium antimonide. So all this you can see that they have very, very small band gap. So that's the reason why electrons inside these materials can move very, very fast. But if you want to make a device by using this kind of materials, and then your device will only operate at a very low temperature, right? Okay, and then so these are basically, you can see, these are the elements in the periodic table, and then you can pick out some of these to form all these kind of materials, right? And then this 2D semiconductor, you can see that and it's many formed between these 6A elements. So you have oxygen, sulfur, selenium, and then tellurium. And then between all other different type of elements and the transition metals and some others all given here. So you can imagine that you can have a wide variety of materials which will have a layer structure in 3D case. So all these materials in principle, you can peel off layer by layer to form this kind of two-dimensional materials, right? And then this kind of two-dimensional materials, you can see that depending on the thickness of the materials, and then you can actually have a different band gap for a same type material. So that's the reason why you can see that eventually you can cover all these different energy range. So basically, if you make a optoelectronic devices, you can realize all these different colors, right? So for example, here you have this tungsten sulfide, molybdenum sulfide, and molybdenum telluride, right? So this one is also tungsten sulfide, but this is 2 layers, and this is 1 layer. You can see the band gap different, right? And they have a tungsten selenide and tungsten telluride, and all of this, right? So, so of course, not just about the band gap, and then for some of the 2D materials, and then you can get some very interesting properties that you cannot get from 3D materials, right? So anyway, I will not go to details. If you are doing research in this field, and then you can read more, right? Okay. So now we come to the scope and the coverage. Sorry, scope of coverage and the assessment of this module. So as I explained that in the first part, I will cover energy bands, and then so basically I explain from single atoms to the material, and then the step by step, and how energy band is formed in semiconductors, right? So once you have the band gap concept, then we can define or we can understand what kind of material will be a metal, and what kind of material will be a semiconductor, right? And so once we understand this, and then the next part we'll look at the semiconductor statistics. So that's because that a pure semiconductor is not very conductive. So that's the reason why it's not very useful for electronic devices. And then to make this conductive, and then you have to introduce controllable carriers, movable carriers, which in a controllable way inside semiconductor. So, and then in this part, we'll talk about how to create carriers and how to control the carriers. So basically talking about semiconductor statistics. And then once you have free carriers inside semiconductor, and then we'll talk about some basic electrical properties of semiconductors. It means that how we can use semiconductor to conduct electricity, right? And in the second part, and then Professor Tour will talk about the optical properties of semiconductors and also low-dimensional structures, right? So, and of course, each semiconductor will have a different optical properties. And then, so what's important here is that when you form a different type of low-dimensional structures, so basically quantum well, quantum wire, quantum box, and then you can alternate or change the property, optical property of the semiconductors, right? And so that you can make a very efficient electronic devices, okay? And the assessment is given here. You can see that we have a CA continuous assessment component. And so 15% from my part, and the other 15% from a Professor's part. So from my part, I will give you an assignment, okay? And then so you will submit a report for the assignment near the end of this semester, right? So I will give you the assignment during maybe after I finish lecture 5. So I will give you the assignment. And then the final exam is 70%, right? So I listed several reference books here. And of course, you can always try to read some other textbooks. And so you can find some in the library, and also you can find some online materials, right? I think that's all about the introduction and about this module. And I hope you get some ideas on why we had to learn semiconductors, and then what are the semiconductors there, right? Since this is the e-learning, so I hope that you can watch the video regularly. Don't leave all the videos to the end of the semester, right? So, and of course, during the lecture time, lecture hour, and then I will set up a Zoom session, okay? So if you have any question, and then you can also ask me during that Zoom session, right? Okay, so that's all about the introduction. And so in next lecture, we'll talk about the lattice structure of semiconductors.